Hello, everybody. Welcome to Miss McGuire online video lectures. And today we are covering bone tissue and the skeletal system. And I'm using OpenStack's Anatomy and Physiology book. So that's a free book that you can access online. And I think that's really great. You don't need to pay lots of money to purchase your textbook. So let's go ahead and begin. Okay, so we're going to start with basic function of the skeletal system, and it will include support of your body. The skeletal system also facilitates movement, protects internal organs, produces blood cells, stores and releases minerals and fat. A little bit of the movement and mechanics of the skeletal system. Your body support your weight, right? They like steel beams of a building. Bones also facilitate a movement. And let's talk about it a little bit more right over here, how your bones facilitate movement. So you're probably familiar with the lever system. If you look at this picture over here, here's a guy trying to lift a heavy load, or this lady is pushing wheelbarrow, or you wanna kind of like use the tongs to crack a nut. So what the lever system does, it actually increase your force, right? So without this lever, or without this wheelbarrow, or without tongs, you probably wouldn't be able to perform any of these tasks, right? So your bones and your muscles work together to create this system of levers. And it's allow you to lift a heavier load without increasing much, force of the contraction of your muscles. So let's see if it all makes sense when we look at this diagram. So the basic lever system includes a fixed point, fulcrum, right? This is the point that does not move. And then you have a load. In this example, this is just a wood or some gravel, maybe. That's whatever you're trying to lift. And then you have your force. In this situation, this is the force applied by a guy or this lady, right? When we're talking about skeletal muscular system, we're talking about force applied by your muscles, right? So because you have this fulcrum, and you're applying force when your muscles contract, you are able to lift the load, right? So over here, you're gonna lift a load, L represent load. Here you're lifting a load, here you're lifting a load. However, it depends where you have this fulcrum, where you have your force and where you have your load. Depends on that, you will have different classes of levers, right? So you have first class lever, second and third class lever. And in the first class lever, the fulcrum is between load and force. In the second class fulcrum, you have fulcrums, then you have force, and in between them you have a load. And in the third, it's vice versa. You have fulcrum and load, and between them you have force. Now, just to make it kind of very quick without going deep into all this mechanics. This arm from fulcrum to a load, let's see if it, so this arm here is called a load arm, right? And this arm is called a force arm. So when you have your force arm, for example, over here, look at your force arm. Right? If your force arm is longer than the load arm, then we call it mechanical advantage. So this type of lever allow you to increase the to lift a heavier load. That's what it says. So that's for the so making your efforts stronger, right? So you can lift a heavier load. That makes sense. So let's repeat it one more time. So if a force arm is longer than the load arms, this is called mechanical advantage. So this make you stronger. This is for strength. Now, if forced arm is shorter, like in a third class level, shorter than the load arm, then this is called mechanical disadvantage. But this allow you to lift the load quickly, right? So that's for speed. So third class level is for speed. Second class level is for strength. And a first class level can be for both strength and speed. So basically, because you have this point of attachment that is fixed point, right? And then you have your force that your muscles contracting, and you have your load that in this example are your bones, right? Or your whole body. How these muscles are attached compared to the fixed point give you either strength or speed or both. And without this lever system, you really wouldn't be able to lift your body parts, right? So they would be really heavy for you to lift. So this mechanics and this build of your body allow you to move your body parts, to lift your heavy bones, to lift your whole body with relatively kind of like medium amount of force. So you don't need to increase force too much to move because of the lever system. Yeah, if it makes sense, right? Okay. We also mentioned that function of your skeletal system is protection. And your bones, they surround your delicate internal organs. For example, your cranium protects your bone. Oh, I'm sorry, your cranium protects your brain. Your vertebral column protects your spinal cord. Your ribs protects your lungs and your heart, right? Your pelvis protects your reproductive organs. So that's a protection. So let me see. Did we cover all the functions so far? So we said that here's our functions: support, movement, protection, production of blood cells and stores of the minerals. So we talk about support your weight, how it facilitates movement. That's we kind of like, hopefully it makes sense. All these levers make sense. This is biophysics, right? So I hope I explain you at least kind of like a basics of the mechanics. I told you, I mentioned protection. And of course, we have a mineral storage, like you store calcium, phosphorus in your bones. You also store fat in your yellow bone marrow. And in some of your bones, in the red bone marrow, in some of your bones, mostly your flat bones, right, in your vertebrae as well. Vertebrae is irregular bones. You have red bone marrow, and this is where you form blood cells. And formation of blood cells is called hematopoiesis. And it's called red marrow, but you form not only red blood cells, you form also white blood cells and platelets. So not just red blood cells. Okay, so we have 206 bones in adult skeletons, and those bones are divided into 5 shape categories. The first category is long bones. Those are cylindrical, they're longer than it's wide, and long bones describe shape, not size. So for example, over here, you have your metatarsal bones or even your phalanges, right, in both your toes and your fingers. They're not really very long, but they're still longer than it's wide. So that's what it says, describe shape, not size. And of course, femur, for example, that's really kind of like long bone. Another category is short bones, and they're cube-like. They're equal in length, width, and thickness. And in a second, we will see the whole table that put all these shapes together and give us some examples. Right, but just over here, for example, your tarsal bones and your carpal bones, those are short bones. Then we have flat bones. They are thin and curved. Those are bones of your cranium or sternum, for example. Irregular bones are not easily characterized by shape. And example would be, for example, your vertebra. Example would be, for example, that. I'm sorry. I mean, English is not my first language, so I do apologize if sometimes I'm kind of like using not the perfect word to describe those bones, but, you know, trying my best, right? So we mentioned irregular bones. Sesamoid bones are small and round, and they found in tendons. For example, patella would be example of sesamoid bone. So here's the diagrams that I mentioned before. So long, short, flat, irregular, sesamoid, 5 categories. And they, because of their different shape, they have slightly different functions. Remember, we talk about complementarity principle. This is when the shape and function, they are interconnected, right? We have different shape, we expect the function to be a little bit different, like long bones, leverage, right? So that's a good, you know, good shape to make a lever. Remember first class, second class, third class that we just discussed, fulcrum, right? So long bones for leverage. Short bones provide stability, support by allowing for some motion. Flat bones, points of attachment for muscles, protectors of internal organs. Yeah, that makes sense. If you have nice flat bone, like in your cranium, that's the best shape to protect those internal organs. Irregular protects internal organs as well. Vertebrae that making your vertebral column. That's for protection of your spinal cord, right? Sesamoid protects tendons from compressive force. And here are some examples for long: femur, tibia, fibula, metatarsals, humerus, ulna radius, metacarpal, phalanges, carpals, tarsals, short bones, sternum, ribs. The ribs is maybe like kind of a little bit confusing, right? Because you're thinking, is it flat or is it long? So ribs are in category of flat bones. Scapula, cranial bones, that makes sense. Scapula is flat, cranial bones are flat. Irregular vertebrae, some facial bones, and sesamoid we already mentioned, patella. Okay, so let's start with the long bone that allow us to see all different parts, right? So the long bone can be divided into 3 regions. So we have proximal epiphysis, diaphysis, and distal epiphysis. Diaphysis is a tubular shaft, and it's composed of compact bone. Epiphyses are ends of bone, and we have also what it's called epiphyseal plate. And this is where you have cartilage instead of bone, and epiphyseal plate allows your bone to grow longer. On this diagram, however, we have epiphyseal line instead of plate, and that means this bone belongs to adult. So when our epiphyseal plate disappears and became epiphyseal line, we cannot grow taller anymore. That is a good thing, right? Medullary cavity, it's right inside diaphysis. Medullary cavity in adults is filled with yellow bone marrow, and this is your storage of fat. Also, your bone is covered by periosteum, and this is connective tissue, dense, irregular connective tissue membrane, periosteum. And inside, like the cavities, like this medullary cavity inside, or spongy bone is covered by endosteum. And endosteum is, similar membrane, dense, irregular connective tissue, but it covers either the cavities or trabeculae of the spongy bone. And you have articular cartilage at the top of your diaphysis, proximal and distal diaphysis. Right? Okay, so let's look at this periosteum and endosteum. So periosteum covers the surface of the bone. So it's shown over here on the picture A. So it contains outer fibrous layer and inner cellular layer. It has collagen fibers. The periosteum also contains blood vessels, lymph vessels, nerves, and the function is attachment point. It attaches to tendons and ligaments. Right. You also, it doesn't say over here, but you do have osteogenic cells in this cellular layer of periosteum. Endosteum, shown in picture B over here. So if you look at the bone over here, right, we have outer layer of compact bone, and then we have spongy bone inside. So endosteum is incomplete cellular layer that cover these cavities inside your long bones or your trabecula of a spongy bone. And it's incomplete cellular layer, and it contains osteoblast, osteoclast. So this is osteoblast. Oh, I'm sorry, this is osteoclast. This is a large multinucleated cell that dissolve your bones. You have osteoblast, right? Those cells that deposit your bone matrix, and osteogenic cells that can differentiate into, and they can divide. Osteogenic cells can divide and differentiate into osteoblast. Right, so endosteum for bone growth, bone repair, and bone remodeling. So that's just pretty much connective membrane covering your bones, either outside or inside. The same as your cartilage, like your hyaline cartilage or your elastic cartilage, they have perichondrium, not periosteum, but perichondrium. So that connective tissue covering, dense regular connective tissue covering cartilage if it's perichondrium, or covering bone if it's periosteum or endosteum. We also have what we call spongy bones, right? And spongy bone is called diploid, right? So that we have layers of trabecula. So all this kind of like structures that look like sponge, right? Let's say this is called trabecula. So we have layers of this trabecula or spongy bone, and on the surface we have compact bone, and then it's also covered by periosteum. Right, and those bones, flat. So this spongy bone you would find in the flat bones, and you will find spongy bone in the epiphysis of long bone. So if you go back over here, you see this epiphysis, that would be our spongy bone as well. Okay. when we cover skeletal system, unfortunately, not only we need to know these 206 bones, we also need to know some features of those bones, some marking. For example, if you have like a humerus, you have a head of a humerus, or you have a crest of your iliac crest, or you have some fossa, you have foramen, right? So all this marking, they have how to say it, they have sense, right? There is a sense in those naming. And if you learn what those marking means, you can easier find them. You can really find them on a bone. So if you know that head is prominent round surface, right? So you're looking at, this round structure, and probably it's going to be on a long bone, right? And probably it's going to be in the epiphysis, somewhere where epiphysis is, because it's a head, right? Or if you see like a fossa, fossa is some depression. So if you see depression, you would say like, maybe it's called fossa, right? Like mandibular fossa, for example, or foramen. If you know that foramen mean a hole, so if you're looking at some holes and like, oh, I should call it foramen, right? So that's why, we're giving you this table. So please take a minute and read through it, right? So pause this video and go ahead and read, because obviously if I'm gonna read all of this video gonna be 3 hours long, right? That nobody wants. So just pause the video, read the names of those markings and their description. Okay, but here we just give you example of selected bone features. So here's, for example, is femur. And where would you find femur? Femur is the bone of your thigh, right? It's even called femoral region. So your thigh in your low limb is made of this big bone, biggest bone in your body, that is femur. So you can see we have a head of the femur, just as I said, just as I told you, it's in epiphysis, right? It's in the proximal epiphysis, and its rounding structure looks like a head. Then we have tubercle over here. We have sulcus. We have fossa. Tuberosity is the rough part of a bone. We have condyles. We have fossa. Now in your pelvis, you have iliac crest. You have fossa. And here we have, let's say, foramen, or fissure, or protuberance of the skull. Right, so that's what we're gonna learn in this class. So not only you will need to learn this as a femur, you will need to know, well, this is, tuberosity. Oh, this is humerus. This is femur, this is humerus. So you have like, you have tuberosity, you have fossa, you have condyles, you have crest, and so on. But that's for our lab part. Okay. Now, composition of a bone. The bone actually has two compounds. It has organic and inorganic part. So organic part of your bone will include cells, obviously, right? Cells are living structure, and they organic. So organic part of a bone includes cells. So what cells? Osteogenic cells, osteoblasts, osteocytes, and osteoclasts. Organic part of a bone also includes osteoid. This is the matrix, organic part of the matrix secreted by osteoblasts. So here's the cells osteoblasts, they secrete this osteoid. And osteoid includes ground substance and collagen fibers. Collagen fibers provide tensile strength and flexibility, and ground substance provides strength. Like example of organic molecules that makes this ground substance include proteoglycans and glycoproteins. That's pretty much protein and sugar together. And we have inorganic part of the bone, and those are mineral salts, mostly calcium phosphate crystals that called hydroxyapatite. And these hydroxyapatites or mineral salts, they make up 65% of bone by mass. And they're responsible for hardness and resistance to compression. So on this diagram, if you look here, you would see that your bone is really like perfect combination of these organic and inorganic parts. Without minerals, it would be too flexible, and without collagen, that is organic part, it would be too fragile. Right? So that's why collagen and mineral compounds are responsible for major functional characteristic of bone. Now, we mentioned that organic part of the bone are cells. So you actually have relatively few cells. You have lots of extracellular matrix, including collagen fibers. But here, let's look at the cells that we have. You have osteoblast, and osteoblasts shown over here. Those are cells that form new bone, found in growing portion of the bone, but they do not divide. They don't divide, but what they do, they secrete the matrix. Osteocytes is this one. Those are primary cells of mature bone located in a lacuna. A lacuna is a pocket of fluid surrounding cell, and they maintain mineral concentration, and they maintain the matrix. No division either. So osteoblast does not divide. Osteocytes do not divide, right? Another cells that we have are, let's say, osteoclast. Osteoclast are bone resorbing cells. So they break down your bone, and by doing it, they allow calcium and minerals being secreted from the bone into your bloodstream, right? So those minerals move to your bloodstream, and sometimes, right, you need your calcium in the plasma of your blood. So that's osteoclast. And osteogenic cells, this one, undifferentiated, mitotically active stem cells. And they become osteoblast, and then osteoblast, when it's in deposit matrix around it, and when it's surrounded by a matrix, it differentiates into osteocyte. So we have osteogenic cells. They divide, differentiate into osteoblast. Osteoblast secreting a matrix surrounding osteoblast, and osteoblast now became osteocytes. So pretty much it makes sense. So you form osteoblast from stem cells, they secrete matrix, now they need to maintain matrix. And to maintain matrix, we have osteocytes. Now, whenever you need to break down your bone, that's the job of osteoclast, right? And osteoclast, those like large cells, almost like macrophages. So those are big cells, multinucleated, that allow you to remodel your bones, if you know, because remodeling means at some point you need to dissolve or resorb the bone to make it, you know, to give it a proper shape. And also osteoclasts are involved in a calcium homeostasis. So we have two types of bone. We already kind of mentioned it. We have compact and spongy bone. So compact bone are stronger of two bone types found under periosteum, found in diaphysis, that is a middle part of the long bone, and it supports and protects your body, right? So functional compact bone is support and protection. The structural unit of compact bone is osteon. So the osteon, if you look at this picture here, or this is histology slide, you see like this circular structure over here. That's the osteon. Let's see if I can. So here's the osteon, right? Or over here, here's the osteon. That's a structural unit. Inside the osteon, you have central canal. So this would be a central canal here, or right there. And you can see inside the central canal, you have blood vessels, you have nerves. And then we have perforating canal. So this, for example, that's a perforating canal. And you also have blood vessels and nerves inside perforating canal. Now, the cells that you find in the osteon is this cell here or here. Those are osteocytes. And osteocyte, so if you have like a cell that is osteocyte, right? So here's my cell. It will be surrounded by a pocket of fluids called lacuna. And you cannot really see over here, but just trust me, those cells are inside this lacunae. And lacunae, they have fluid. You know, bone matrix is very hard structure. It's mineralized, calcified, mineralized. So it's a really hard structure. And cells, animal cells, and we are in animal kingdom, they can only survive if they are surrounded by fluid. So you cannot just kind of throw these osteocytes right inside that bony matrix. They need this little lake around them that is called lacuna. Lacunae is plural. Right, and so we have this osteocytes, we have this lacunae, and then you see here, you can see like, you know, those little lines look like little hair. This is called canaliculi. And what canaliculi do, they connect two lacunae together. So that would be canaliculi. So that's allow for nutrients and oxygen. It allows nutrient and oxygen to move from your blood, right, from blood vessels to those cells through this canaliculi. Lamellae are these concentric structures. So here's, let me see, for example, this one circle, it's one lamella, and you have another lamella, and here's another lamella. And those are really not just the circles, they are like cylinders, right? Like a cylinder inside another cylinder inside another cylinder. And that's what those lamellae make osteon. Spongy bone, another name is cancellous bone. And we also have osteocytes in the lacunae. So here we see the lacuna and the cell is inside. And instead of osteon, we have trabecula. So those are trabecula and they appear random, but they form a long stress line. And spongy bone make bone lighter. And also in the cavities in between this trabecula, we can store a red marrow, and remember a red bone marrow for hematopoiesis. So we can form blood cells within this red marrow. We do have blood and nerve supply, and blood vessels and nerves enter a bone through the nutrient foramen. It's a small opening in diaphysis. Nerve sends pain, regulate blood supply, and what blood does, it brings nutrients, oxygen, removes carbon dioxide and waste product from those osteoblast, osteoclast, osteocytes, right, and stem cells. So all those living cells, they require oxygen and nutrients, right? And through metabolism, they produce waste products that need to be removed. That's why we need blood supply. Actually, your bones are very vascular structure. If you break a bone, you're gonna bleed a lot. Hopefully you will never break a bone, but if somebody breaks a bone, they're gonna be a lot of bleeding. Compared to cartilage, cartilage is avascular. And disadvantage is that cartilage is really difficult to heal. If you have like rich blood supply to an organ, that organ heals way better. Cartilage doesn't have blood supply, so it's received nutrients or oxygen by diffusion, and it's way harder for cartilage to heal. Okay, so now if you get to this point, then good for you. We're gonna skip part of this PowerPoint just for a minute, and we go straight to here, and I will tell you why. Because this book is anatomy and physiology book, and I have both anatomy classes and anatomy and physiology classes. So if you are in anatomy class, this is for you. We're skipping those slides, and we only cover what you need to know. Because in the middle of the slide, we have a lot of physiology. And if you are in anatomy and physiology class, I will continue this lecture after I'm done with anatomy part. So this part, homeostatic imbalances, this part is for both anatomy students and anatomy and physiology students. I don't know, sometimes I feel like, do I really explain it right? I mean, does it make sense? I hope it does. So it doesn't matter if you anatomy or anatomy and physiology student, this is for you. The last part of this lecture will be only for physiology, for anatomy and physiology students. Hope it makes sense. Okay, you let me know if it doesn't. Now, homeostatic imbalances. So we will look at some diseases related to skeletal system, and the first two are osteomalacia and rickets. This is when calcium salt are not deposited, and if calcium is not deposited, the bone can't mineralize, so the growth plate can't mineralize, and the bones, they lose their strength, right? So they became like easy to be deformed. And for example, rickets, it's a childhood disease. And now when the child is growing and you know, became a bigger, gained some pounds, but bones are still soft, then some bone, they can be deformed, like shown on this x-ray. This is called bowed legs. So this is the characteristic of rickets. Also, people with rickets will have other bone deformities, and this is again because calcium is not deposited, so the bones are not getting mineralized and are not getting stronger, right? And osteomalacia is similar to rickets, but it's happened in adults. Well, in adults, you might not see this bowed legs or deformities because during, you know, this childhood and adolescence, if the patient had everything, you know, calcium, salt, and normal concentration, no vitamin D deficiency, then the bones will already form, and then it would be difficult to bend them this way later in your life. Right, so anyway, osteomalacia and rickets are similar diseases. Both are caused by lack of calcium salt deposition in a bony matrix. The difference is rickets happens in the childhood, osteomalacia in an adult age. And cause can be vitamin D deficiency or insufficient dietary calcium. So either the patient does not have a good amount of calcium, or they don't have enough vitamin D that is required for this calcium absorption from your digestive system to your bloodstream. So you eat food, it's rich in calcium, but calcium is just not absorbed into your blood and it's not deposited to your bone matrix. Osteoporosis. Osteoporosis, loss of bone mass, bone resorption outpaces deposit. And here you can see normal bone and osteoporotic bone. You see how it became more porous. And because of that, of course, it's more fragile. It's more susceptible to fracture. And the bones that mostly affected are spine and neck of a femur. Now, risk factor include lack of estrogen. That's why osteoporosis is more common in older females, because when older females go through menopause, the amount of estrogen drops, and estrogen is needed for normal bone functioning and formation, especially for deposition of bone matrix. Another risk factors include calcium or vitamin D deficiency, petite body form, immobility, low levels of thyroid stimulating hormone, or diabetes mellitus. So over here you can see very, like a classic sign of osteoporosis in older females that we call hunchback. So again, this is a normal vertebra, and here we have one vertebra affected by osteoporosis. You see how the bone is dissolved here, and because several vertebrae losing their shape, right, and they became like thinner, so you loses this bone mass. The back has this curve that we called hunchback or kyphosis. That's a scientific name. Treatment and prevention include calcium, vitamin D, fluoride supplements, increase of weight bearing exercises through life, estrogen replacement, because we just said that low estrogen level affect bone formation, and also some drugs that inhibit osteoclast bone resorption. And the last disease we're gonna talk in this lecture, of course, it's not the last disease of your skeletal system, just for this lecture, is Paget disease. When we have excessive and hephosarc bone formation, so you actually form more bones, but those bone is very fragile. It's mostly made of spongy bone. You reduce the amount of compact bone, right? So it says Pagetic bones has very high ratio of spongy to compact bone and reduced mineralization. So you grow more of a bone, but this bone is actually easy to be damaged, to be broken. And especially the bones that are affected are spine, pelvis, femur, and skull. So you can see this lady over here. That is actually a photograph used with permission of the patient. That you see how she's affected by the disease, this increased mass of a spongy bone growing, and it's very susceptible to fracture. So case is unknown, probably viral case, and treatment include some drugs that will cause apoptosis of osteoclast. Okay. That's, I think, that's the last slide over here that I have for anatomy students. So now I'm going back to physiology part. So I'll try to do it kind of quickly. I don't want this lecture to be too long, so we cover this. So now if you are in my anatomy classes, that's the end of lecture for you. If you are in anatomy and physiology class, let's cover some physiology. So how bones are formed? Obviously, you're not born, I mean, you're born with your bones, but during embryonic development, everything starts with one, cell, nice and soft. There is no way it's a bone. Then you remember those kind of like those cells divide. When we have enough cells, we start forming embryonic tissues. At some point of time during embryonic development, about week 8 of the embryonic development, we start formation of bones. Now, there is 2 ways for your bones to form, and it's intramembranous ossification, so it's right here, intramembranous ossification, and endochondral ossification. We are not going into detail. We're going to cover it very quickly. So when we're talking about intramembranous ossification, first membrane is formed. So it's a dense, irregular connective tissue membrane. So we have a membrane, and the cells inside this membrane are mesenchymal cells. Those are stem cells. They can differentiate into different cells. So we have this membrane, right? So if you look like an embryo that is 7 weeks old, you would not find this frontal bone, for example. If you can squeeze it, you can push it, that's just a membrane. That doesn't give you much of a protection, but it gives you flexibility. So it's allow your brain to grow. That's good to have this membrane at the beginning, right, of our development. But then when we are born and, our brain is not increasing in size that much, then we want a bone instead of membrane, right? So we start with the membrane and those mesenchymal cells. Now, this mesenchymal cells gonna differentiate into osteoblast. Remember, they are undifferentiated stem cells, so they can become different type of cells. So in this situation, with some, signal received, they differentiate into osteoblast. And this osteoblast, they kind of in the same spot that is called ossification center. So it's not just like everywhere, right? It just in a particular area of this membrane, we start differentiation and form ossification center. Now, when we have osteoblast, you know what osteoblast does? It starts secreting matrix. So it secretes matrix, osteoid, right? And this osteoid surrounding osteoblast, and osteoblast became osteocytes, right? Next, what happened? At the same time, you have development of blood vessels, angiogenesis. So the blood vessels are growing inside the ossification center, and osteoid is deposited around those blood vessels. And that's why it formed this trabeculae, right? So trabeculae are formed because the bone matrix is not deposited in layers or in like circles. It's deposited just along this blood vessel, forms this irregular pattern that we call trabecula. And we have the spaces in between. And inside those spaces, you see how we have a lot of blood vessels. So those blood vessels, those vascular part of your body form red bone marrow. So all these blood vessels and form red bone marrow, where you will have then formation of blood cells. All right, so we form this trabecula. Now, so this mesenchymal sites on the surface, they form periosteum. Just deep to this periosteum, we still have osteoblasts. So like inside, we now have osteocytes. But this osteoblast, just deep to this periosteum, it forms compact bone. Right? So, and we have this, bone that formed by intramembranous ossification that will have spongy bone inside and compact bone on a surface, and it will be covered by periosteum. Now, what bone is that? That's a flat bone. So your flat bones are formed by intramembranous ossification. So those are bone of your head and your clavicle. So the clavicle is formed by intramembranous ossification. Now, so here we're pretty much done, right? So, so those are the last bone to ossify, flat bones of a face, and they're formed by intramembranous ossification. Make sense? Another type of ossification is endochondral. That means that instead of membrane, so intramembranous, membrane is formed first and then bone. Endochondral ossification, cartilage model is formed first and then bone. So what's gonna happen over here? We have also mesenchymal cells, but instead of making membrane, mesenchymal cells first differentiate into chondrocytes. And chondrocytes form cartilaginous precursor of all the bones. So you pretty much like, I don't know what bone is it, let's say it's your femur, right? Your future femur. So instead of forming a bone of femur, you form femur made of hyaline cartilage. So the mesenchymal cells differentiate now into chondrocytes. They form this hyaline cartilage model, right? Then we have membrane covering cartilage that's called perichondrium. So you have chondrocytes, but you still have some mesenchymal cells stays inside of the this cartilage, and they differentiate into osteoblasts, and they start depositing this structure over here. If you see like this, and over here, and this is called the bone collar. So this is a bone collar. So that's the first bone that is formed, right? Kind of like in the middle of diaphysis. Now, when this collar is formed, cartilage cannot receive nutrients and oxygen by diffusion anymore, because bone is, mineralized and it's calcified. So it's a strong structure, so we cannot diffuse through it. So now this cartilage start dying off. So the cartilage here, because of those mean mesenchymal cells, right? So mesenchymal cells form cartilage. Okay, good. Then some mesenchymal cells differentiate into osteoblasts. And this osteoblast start secreting a bone, making a bone collar, killing those chondrocytes. Now, when those chondrocytes dies, obviously you start having a cavity right inside. So you see, you have like a cavity inside, and you and those osteocytes continue to depositing bone matrix. So you have like a spongy bone formed. Then you have artery invading this area, and together with the blood, guess what else is delivered? Our osteoblast, osteocytes. Osteocytes, osteoblast and osteoclast. And they starting pretty much depositing the bone matrix over here. And so now this area is called primary ossification center. So the long bone start as ossification, a bone formation from diaphysis towards the epiphysis. So you form the bone collar first, right? And then you continue to building a bone and replace cartilage with the bone from center to the periphery. In some bones, then we have formation of secondary ossification center in the epiphysis, and the process repeats. So sometimes we have two secondary ossification center if it's a really long bone, or just one ossification center. But you start forming bone in the middle, and then you start formation of bone in the center of epiphysis. So you end up with bony structure in diaphysis, bony structure in the middle of epiphysis, and epiphysis will be surrounding by cartilage, right? And the outer cartilage we call articular cartilage, and this inner part of the cartilage, right there, this is our epiphyseal plate that will allow your bones to grow longer even after you are born, right? So that's endochondral ossification. So just for a summary, two types of ossification for flat bones and clavicle, intraosseous, when we start with a membrane, and this membrane is replaced by bone, or endochondral ossification. All your bones below your skull, except of clavicle, are formed by endochondral ossification. And then we start with a hyaline cartilage, and then hyaline cartilage is replaced by bone. Right, so that's just kind of like a brief summary. And then we have some diseases, they genetic, and they either affect your endochondral ossification or intramembranous ossification. And this is called achondroplastic dwarfism, right? So shown over here, Peter Dinklage, the guy who was an actor in the Game of Thrones. So he has genetic conditions that affects his endochondral ossification. So the bones do not grow longer, and they kind of like, so you can see that he had like a shorter arms and legs. And this guy, Gettin Matarazzo, this guy has a condition, genetic condition called cleidocranial dysplasia. And this is some problem with intramembranous ossification. Okay, now also bones can grow in length until you have this epiphyseal plate. So epiphyseal plate is made of cartilage, so that's a hyaline cartilage. The bone cells, they cannot divide. Cells of the cartilage, they can divide. So when they divide, obviously you have more cells and the structure is growing bigger. So your bones can grow longer, and when they grow longer, we call it interstitial growth. And we can have this interstitial growth until we have this epiphyseal plate. When epiphyseal plate is gone, all this cartilage now became a bone. We have a line instead of plate, then bones cannot grow longer anymore. Right, so epiphyseal plate is area of bone growth in long bones. Right, so you can see the cartilage grows over here. So cartilage, chondrocytes divide, they divide, so you increase the amount of cartilage, but at the same time, this inner surface of cartilage is replaced by bone. The same over here in epiphyseal plate. The cartilage grows here, right? And in this area right there, it's replaced by bone. So with time, this epiphyseal plate is getting thinner and thinner and thinner until it disappears. So when we look at this epiphyseal plate, right, so here's the representation of the plate. It has several zones. So it has, so here's your cartilage, right, with chondrocytes. And then the cartilage, those chondrocytes, they start dividing and they form proliferation zones. So you can see how they divide by mitosis, forming more and more cells. So you have more and more cells, obviously the structure is getting thicker. Then you have maturation and hypertrophy zone. When this chondrocytes, they became larger, so they became bigger. So that's our hypertrophy. And they accumulate lipids, glycogen, right, and other minerals over here. I mean, not minerals, and rather organic molecules, right, and calcium, plus calcium. Then we have calcified matrix. This is where calcification happens and cells start dying. So they pretty much, like, you know, think about these chondrocytes. So they live perfectly here in reserve zone. Then they start dividing. You were thinking, you dividing, you grow bigger, right? For what? Well, just to die. So they divide in proliferative zone. They get bigger in maturation and hypertrophy zone. But then they start accumulating lots of calcium. And you surrounding yourself with this, you know, calcium around you, you get less and less nutrients diffuses to you, less oxygen. So you start dying. So those chondrocytes die. And when they die, they are replaced by bones, right? So then if cartilage is dead, what's gonna happen? We have osteoblasts that will deposit the bone matrix in a place where cartilage is dead. That makes sense? And it's called zone of ossification, where we have deposition of bone matrix now. So we have calcification and then ossification. And ossification is making all this, you know, inorganic part of bone matrix. So the cartilage, pretty much the job of this cartilage, chondrocytes in epiphyseal plate, is to divide, increase in size, make this, you know, part of your bone longer, and then die and be replaced by bone. Okay, this is our interstitial growth. So this all I already described to you, so you can read it again. And here's the histology slide that show us, you know, the same zones. We have a resting zone, right? And then we have proliferating, hypertrophy, then calcification zone, right? And finally ossification zone, where now we have bones, bone instead of cartilage. So we have cartilage here, and then cartilage is replaced by bone, right? And you see, like, cartilage is avascular. So whenever you see vascular invasion, that means this blood gonna bring your osteoblast bone cells, and they start secreting matrix of the bone and replaces dead cartilage, because you don't want a dead stuff in your bone, right? But the problem is osteoblast cannot divide on its own. So they rely on cartilage to divide and grow. Then pretty much those cartilage kills itself, right? It accumulates so much calcium, they are dying, and then bone replace cartilage. Hope it makes sense, right? Doesn't make that much sense, but I guess we need to sacrifice cartilage in order to have new bone. We also can have apostitial growth. Apostitial growth, the bones are growing wider, and it's also for remodeling. And so here what happened, actually osteoblast, right, start secreting more matrix, and it's formed the bony ridges along the blood vessels. And when those bony ridges meet, we have this groove containing on blood vessels. Now this osteoblast right here, right? So this osteoblast, they deposit more bony matrix, and this canal became narrow, right? And you form new, kind of like new osteon. So here's a new osteon is formed, right? So again, osteoblast just beneath over here, beneath the periosteum, secrete the matrix, and matrix forms this ridges, and we have like so much matrix that those ridges meet, and they enclose this central canal, and then central canal became narrow, and we have new osteon formed. So you form new osteons, the bone getting wider. And this aposticial growth is mostly for bone remodeling. So growth in the diameter and bone remodeling that happens through your entire life. So every year, 5–10% of your skeleton is replaced by new bone. So that's really good. That means that it doesn't matter what age you are, you can actually increase your bone mass. So if you exercise a lot, if you have these weight-bearing exercises, your bone can become stronger. That's a good thing. Very quickly, type of fracture. Fracture means broken bone, and it can be classified based on, type of fracture. Is it open? Is it, kind of sticking through your skin or not? It can be classified by complexity, location, other features. So really classification of bone structure is pretty complicated. So if you look at this diagram here, you can see like we have transverse fracture, oblique, spiral, comminuted, impact, green stick, open or compound, closed or simple, right? So take a minute, pause here, read the description, right? So over here, I can just kind of show you, like, for example, this is closed, this is open fracture, this is transverse, because it's kind of like just kind of cut, the bone is broken just across. All right, here you have a spiral. Comminuted means the bone is broken into several parts. Impact, usually like one part of the bone kind of shifts above and below another one, so that would be impact. A green stick, when the bone is not broken all the way through, usually happen in kids. An oblique, this fracture is under an angle. Okay, and bone repair. So bone repair includes several stages. So when you have this fracture, when your bone is broken, you start with hematoma. And because your bone tissue is very vascular, so you have a lot of blood leaking out, then blood will clot. Those cells, bone cells will die, so you have a hematoma, and then you have a clotting of the blood. Then you have a formation of calli. Calli is plural, callus is singular. So you have internal and external callus, and this is fibrocartilaginous matrix. So you fix your bone with the cartilage first. I guess this cartilage help bone a lot, right? So you fix this fracture with the cartilage and fibers and collagen fibers. And then, as usual, this cartilage start dying. It helped your bone, but it start dying because again, it has too much calcium deposited around it. So when those chondrocytes of the calli die, they replaced by bone. So it's replaced by trabecular bone, spongy bone, and it takes like several weeks. And then you have remodeling and deposition of compact bone on the surface. remodeling of all these calli. So you need to dissolve a little bit bone on this, a little bit of bone matrix here, and maybe add it at another, area. So your bone pretty much, hopefully, will look similar to how it looked before the fracture. I just want to mention that bones are so good at repair process. When they repair themselves, this part became so strong that very, very rare you would break your bone at the same spot. So bones are really good at repairing. And again, they need help of cartilage to do it. Now, here's kind of the basics. Exercise will stimulate deposition of mineral salts and collagen. It will make your bone thick. It gives you great density of your bones. You also need calcium, vitamin D. Vitamin D is needed for absorption of calcium from your food to your bloodstream. Vitamin K that supports bone mineralization. And here's we will have two tables, right? So again, pause this video and read about all these vitamins and minerals and how they affect the health of your bone, right? So here you have a calcium, vitamin D, vitamin K, magnesium, and different hormones here, right? So that's all affect the health of your skeletal system. Kind of the last slide. So don't forget to pause the video and read these two slides, right? Because again, this video is getting longer than 1 hour. So you guys need to do some of work on its own. But I want to very quickly, this is the last slide. So I promise that's the last one. Talk about calcium homeostasis. Well, calcium homeostasis is so critical for your normal body functioning. It's not only for your bone formation. You need calcium for muscle contraction. You need calcium for secretion. So your glands cannot secrete stuff without calcium. You need calcium for normal functioning of your neurons. So neurons need to secrete neurotransmitters and send these electrical impulses. And they must have normal amount of calcium to do it, right? So your normal calcium level in your blood is about 10 milligrams per deciliter, right? So, and 1 deciliter is 100 milliliters. So it's a kind of like glass like this, like a glass, that would be 100 milliliters. So you need 10 milligrams. Now, if the calcium level goes up, right, more than 10, then thyroid gland release calcitonin. Calcitonin affects osteoclasts and it inhibits them. And remember what osteoclasts do? They dissolve your bone. So osteoclasts constantly dissolving your bone, and all this calcium from your bone goes to your blood, So now we have enough calcium already. So we need to inhibit osteoclast, right? So that will be our calcitonin. Also, we wanna decrease of reabsorption of the calcium from by your kidneys. What kidneys does, so first you filter out this calcium and then you reabsorb it back to your blood. That's what kidneys do. So you want to decrease this reabsorption because you don't want calcium in blood, right? You already have high level. So high level of calcium means let's inhibit osteoclast. Let's leave this calcium in your urine and get rid of it. So no reabsorption. And hopefully by doing it, we decrease calcium level in blood and we restore the balance back to normal. Now, if calcium level drops, then your parathyroid gland release parathyroid hormone. And the parathyroid hormone also affect osteoclast, but it's promote their work, right? Like, okay, so osteoclasts became more active because of this hormone and they start this dissolving your bones more and more and secreting more calcium in the blood. Plus, your kidneys start taking calcium from your, it's not called urine, called filtrate still, but just to make it simple, from your urine. You don't want a calcium in your urine. You want your kidney to reabsorb this calcium back to your blood, right? Plus, you want to increase reabsorption of calcium in your small intestine via vitamin D synthesis. So here you have it. You have low calcium level. That's really dangerous, right? It's called hypocalcemia, low calcium. You cannot coagulate your blood. Your heart is skipping beats. Your bone became brittle, right? You don't want this hypocalcemia. So what do? Start, resorbing the bones, release calcium into blood. Start reabsorbing calcium from filtrate. So it's not in your urine, it's in your blood. Start absorbing more calcium in your GI tract. Synthesize more vitamin D. Hopefully calcium level goes up and you restore your normal balance. And what I mentioned over here, when you have too much calcium, it's called hypercalcemia. And that make you tired, constipation, confusion. So neither one is good for you. And that's why, thankfully, to our endocrine system, right? Thyroid gland, parathyroid gland. By the way, parathyroid gland is more important in this homeostasis. But thankful to these two hormones, you can restore your normal calcium level to 10 milligram per deciliter. Okay. As I promised you, this was the last slide, and I cover bone tissue and skeletal system, and I hope it was helpful. Thank you for watching.